All right, so how do we extract meaningful, significant numerical data from graphical data? Because oftentimes you're not presented with a table of numerical data where it's really easy to identify how many significant digits are there. But instead you have a series of data similar to what we have here. So I've got two graphs here. I grabbed these just straight out of the textbook. The first question you have to ask is, what is the author trying to convey to you? Are they trying to convey to you specific numerical data, which is essentially meaning this could be also represented by a table, or are they just trying to convey a functional relationship? And the two examples here represent either of those scenarios. So you can see the one on the right here. Here, the delineations for the x and y variables are pretty coarse. So there's not a lot of very specific information that we could extract from this set of data. We could get estimates at any one of these points, but because this is a curved plot that changes pretty rapidly with not very easy gradations to measure, this is more an attempt in the authors to represent the functional relationship between variables x and y. In contrast, if we look at the plot to the left, we can see a grid. We can see much more sort of space between key markers in terms of delineation on both of the axes. We can see a bold line at 0, and it becomes much easier to extract meaningful, significant digits from the plot here. So how do we do this? Well, if you have gradations here, what you can do is you can read the number. So let's say we want to extract, I don't know, a value right here. What we can do is we would say, okay, that's 10 mils. That's 11, 12, 13, 14, 15, 16, and I think that's it. So 16 milliliters. So it's between the 16 and 17 marks here. So it's going to be 16 point something. And that next digit is still significant because there's something that we can still interpret. If we zoom in a little bit, we can interpret that red dot is a little bit closer to 16 than it is to 17. So it's not completely random, that number, which means it's still significant. So we would make some assertion that says maybe 16.4. And those three digits would be significant. Anything beyond that would be insignificant. So you can always guess one digit past what's absolutely defined by the gradations of a graph. That's also going to be true when we're thinking about doing this with instrumental data. So if you're reading a curve or reading a value off of, say, a burette, which I'm showing to the right, so we talked about this in the first video. So burette is an accurate and a precise way to measure and deliver volumes of liquids. If we look at the gradations here, these are in milliliters. So we have, say, 18 milliliters here, 19 milliliters here. You can see, let's just negate the red lines here and just focus on the green one that's here. Oop, that's a thick line. And what we can see there is we can estimate where exactly that line crosses. And the gradations here are in 0.1 milliliters. So we know for sure the first three digits. We know with absolute certainty what the first three digits are. And the fourth digit becomes our best guess based on where the meniscus lies between the most fine gradations. So in this case, that line, that meniscus, if you're looking at it directly side on here, lies exactly on the line. And so the fourth digit estimate would be a 0 here. So we'd have 19.70, all digits being significant, the first three being absolute, and the last one being our best guess, which is still not random, which makes it significant. So that's how you would read a scale in the same way that you would read a graph, and the same would be true for instance, a scale like this. This would be an analog scale on an absorbance spectrometer. So you use these in general chemistry like a Spec 20. These were the benchtop spectrometers. You can see that there may be merit in choosing a scale even, depending on what you're trying to measure. So it's a lot easier if we, even though transmittance and absorbance are related to each other functionally, and we'll talk about this later through the relationship negative log t is equal to absorbance, which is why you get these two scales. It can be easier to make your measurement first in absorbance in this case because it's easier to tell where the gradations are. So in this case, we have 0.2 here and 0.3 here. So each one of these lines here would be, let's see, would be, it looks like there's about 7 lines there, so this isn't a great example, but it would allow you to estimate 1 digit past what you know for sure on the axis in terms of the absorbance. So this would allow you to get 3 significant digits from the absorbance scale.